Light is everywhere, the most famous example being the sun. The sun gives us both light and heat in the form of electromagnetic radiation. The light bulb has also become one of the most common household appliances, although it doesn't quite look like this anymore, and any display you might have in the form of a TV, laptop, or mobile phone emits light. Let's consider a torchlight, which emits a beam of light, and we'll take a look at a single ray. Each ray of light is composed of an oscillating electric field and magnetic field, both of which oscillate perpendicular to each other and mutually perpendicular to the direction of propagation or movement of the field. Let's take a look at frequencies. Frequency tells us how many oscillations per second the wave is doing, and it's measured in a unit called hertz. So in this case, the red wave has a greater frequency because per second it's doing more oscillations than the blue wave. And all the combined frequencies of all electromagnetic radiation gives us a spectrum known as the electromagnetic spectrum. Along these spectrum lie gamma rays and X-rays and UV light, which have high energy, and low energy light like microwaves, radio waves, and infrared. And in the middle of this spectrum, roughly speaking, lies visible light from 740 to 380 nanometers. Now, wavelength is simply the distance between two consecutive similar parts of the wave. What do I mean? Take any part of the wave. For example, you could take the topmost peak and measure the distance from that peak to the next following peak, and that would be your wavelength. And you can pick any part of the wave and measure the distance to the next corresponding same part, and you get the wavelength. And why am I giving visible light in terms of wavelength? Well, because I can't give it in terms of frequency or wavelength. It's actually the same thing. You see, because frequency times wavelength equals a constant, and that constant is the speed of light itself, if I give you the frequency, you can easily figure out the wavelength and vice versa. So when we're describing any electromagnetic radiation, giving the frequency or wavelength is acceptable. Only in vacuum, however, because in other media, such as water or glass, the wavelength changes, but the frequency does not, which is why we typically use frequency, but the wavelength is also valid if light is being considered in a vacuum. And these different frequencies or wavelengths of light are what we perceive as color. But that's not the question I want to answer today, because we generally know where color comes from the different frequencies of electromagnetic radiation. I want to answer, why are certain objects a certain color? Why do certain objects reflect certain electromagnetic radiation, but not other frequencies of electromagnetic radiation? So to begin, let's take a look at this t-shirt. We know that sunlight hits the t-shirt and reflects off of it and then enters your eyes. Now let's take a look at this at an atomic or microscopic scale. We know the t-shirt has a regular arrangement of atoms, and we'll look at a ray of light striking and reflecting off of it. Each atom has a nucleus with electron shells around it, and these electron shells represent different energy levels in which the electrons reside. The electron energy level goes up or increases as we move outward from the nucleus. We say this as the potential of the electron increasing, which is a fancy way of saying it's gaining more energy. Now let's take a look at a single photon of light. What does it mean for this photon to have a particular frequency? Well, it basically means it oscillates up and down along a wave pattern a certain number of times a second. And the energy of this photon is given by Planck's constant, a special constant, which is equal to 6.62 times 10 to the power minus 34, multiplied by its frequency. So more the frequency means more the energy. Now let's take a look at different colors of photons, so to speak. Each photon, which we observe as being a different color because of the way our brain interprets these different frequencies, is just a regular photon with a varying frequency. And this frequency also determines the energy of the photon. So more bluish colors like blue and purple have greater energy, while reddish colors have lower frequencies and lower energy. So if an atom is hit by a photon with this energy, it jumps to a higher energy state. And this energy difference between these two states is the same as the energy of the photon which strikes it. Let's say we have an electron which has a 3 electron volt difference between itself and the other energy level, the outermost one, and a photon hits it. If the photon has exactly 3 electron volts of energy, the electron will make the jump. Now let's consider another electron But this time the photon's energy does not match the energy difference. Then the photon will simply get reflected and the electron won't absorb the photon and jump to the next energy level. So a photon will either be absorbed or not absorbed depending on its own energy with relation to the energy difference between the orbitals of an atom. And that is why different materials appear to be different colors, because different materials are made up of different atoms which reflect and absorb certain wavelengths of light. Our brain is simply taking these reflected rays of light or different colors of light and compiling them together to produce a single color. In fact, the color magenta or pink does not really exist. Magenta is simply the combination of when red light and blue light both hit your eyes at the same time. Our brain simply made this color up to interpret both blue light and red light hitting our eyes at the same time. There is no particular wavelength which corresponds to the color magenta, and this is mostly true in our daily lives. Colors we see are not pure. They are not individual pure wavelengths of light. There are many wavelengths or many frequencies hitting our eyes which our brains compile to give a single color. And that's why your computer screen can play this trick on you, where each pixel is only red, green or blue, but yet by varying the brightness and intensity of these pixels, it can show you millions or maybe even billions of colors if you have a high quality monitor. Thank you very much for watching. I hope you enjoyed this video, watching it as much as I did creating it. Please hit the like button if you like this video or you learned something new, and please do consider subscribing as it does help support starting channels like this one. I hope you have an excellent day.